In this video, I wanted to give a little bit of intuition about what exogeneity means visually. So I want to start with, for one, making sure that we're strong on the distinction between U and E. So for E, the residuals, we have some data points. And maybe they look a little bit like this, and we can draw a line of best fit that looks like this, something like that. And the residuals are the distance between the line of best fit, which is estimated, and the values for y. They're these vertical distances between the estimated model and our data points. So that's EI. And we've also proven in the past classworks that the sum of EI will always be 0. And that's enforced by how we choose. We chose beta hat 0 and beta hat 1 in order to make this true. So that will always be true. Versus, let's talk about U, the unobserved disturbance. And over here, we're going to have the true model. So this is not the estimated line of best fit. This is the true line of best fit. And let's say X takes on a 1, a 2, and a 3. And the true model is that Y is some true beta naught plus some true beta 1 X plus U. And so if our data point is here, and then here, and then here, the U is the vertical distance, but it's not the vertical distance between our data point and the estimated line of best fit. It's the vertical distance between our data point and the true line of best fit, which is this thing, right? So if exogeneity holds, here's our formula or our equation for exogeneity. It means that the expected value for U for any given observation, given X, is 0. So that means that U has some kind of distribution, right? Maybe the distribution looks like this. And if the conditional expectation of U is 0 given any X, it means that this distribution is centered on this true line of best fit for any given value of X. A violation of exogeneity would look like this. So if in the case where exogeneity doesn't hold and we have the conditional expectation of U given X is not 0, then it would look something like this. X, Y, a true line of best fit like this. And suppose that the distribution of U is, not centered on that line of best fit here, or here, or here. So we're going to get values for U that are maybe something like this, and then this, and then this. And every time we estimate this model, U could kind of dance around, but it's only going to be in this distribution. So every time we observe these data points and we draw a line of best fit, we are going to likely draw lines of best fit that look something like this. And beta hat 1, that estimate for the slope of this line of best fit, is going to be way off. We might estimate it to be negative when in truth it's positive. So that's some intuition about why exogeneity is so crucial to this proof that OLS estimates for beta hat 1 are on target, that they're unbiased.